How many of these 10 questions on chemical bonding can you get right in under 10 minutes? Let's find out. This question focuses on ionic compound. We need to name Al2O3. Al is a metal and O is a non-metal, and together they form ionic compound. When we name ionic compound, the metal is named as is. Therefore, aluminum will just be aluminum. And for oxygen, it's just on its own. So that's a monoatomic anion, and we need to change its name so that it ends with IDE. Therefore, oxygen will then become oxide. So the name for Al2O3 is aluminum oxide. This is a question involving ionic formula. We're given the formula XF2, and we can reverse engineer to figure out the charges of the ions involved. So XF2 came from X2 plus and F minus. So the charge on metal X is 2 plus. We know the formula for phosphate ion is PO4 3 minus. Now we're going to combine these two ions together. To write out the formula, we start with the cation, which is X, and then we cross over the 3 from phosphate, and then after that we write out the anion, which is PO4, and then we cross the 2 over to the other side. Now this 2 is meant for the entire PO4, so therefore we need to include this bracket. This is the formula for phosphate X. This question is on boiling point trend, which focus on intermolecular forces. If we look at these 4 compounds, they're all from group 16. Therefore, as you go down the group, the molecular weight increases, and so we expect the boiling point to increase as well. However, since boiling points depend on strength of forces which exist between the molecules, let's consider the intermolecular forces that's present in each of them. The stronger intermolecular forces will result in higher boiling point. All of them have dipole-dipole interaction because there's permanent dipole between the hydrogen and the atom. Since oxygen is a highly electronegative atom, it is also capable of hydrogen bonding as well. Since hydrogen bonding is much stronger compared to dipole-dipole, H2O will therefore have the highest boiling point, and that makes A the correct answer. This question focuses on bond polarity. Covalent character depends on the electronegativity difference. The smaller the difference of electronegativity, the more covalent character it has. Notice all these compounds has chlorine. That means we can just compare the electronegativity of the metal. The larger the electronegativity of the metal, the smaller the electronegativity difference, and that means the higher the covalent character. Based on the periodic trends, electronegativity increases as you go up a group and across a period from left to right. That means lithium is more electronegative than sodium, and beryllium is more electronegative than lithium. This means that the covalent character increases from NaCl, LiCl, BeCl2. This question is asking on the polarity of molecule, and in order to answer that, we also need Lewis structure and VSEPR theory knowledge. To answer the question, we're going to start off with the Lewis structures. It's worth noting that sulfur and xenon can accommodate more than 8 electrons, while boron and beryllium need lesser than 8 electrons. These are the exceptions to the octet rule. From the Lewis structure, we figure out their geometry using the VSEPR theory. Now, the molecule is polar if there are different terminal atoms or unsymmetrical lone pairs on the central atom. All 5 of the molecules have the same terminal atoms, so we're going to focus on the lone pair. Notice that XeF4 has 2 lone pairs. However, due to its geometry, the lone pairs are symmetrical, opposite from each other, while SF4 has 1 lone pair, which makes it unsymmetrical. Therefore, SF4 is polar. Next question is on Lewis structure and VSEPR theory. We're comparing the bond angle in CH4 and XeCl4. So we draw out the Lewis structure, and based on the Lewis structure, we figure out the geometry. So CH4 is a tetrahedral and XeCl4 is a square planar. The bond angle that's present in tetrahedral is 109.5, whereas the bond angle between Cl, Xe, Cl, each of it is 90 degrees. And that's just because you have 360 divided by 4, so you get 90 degrees, making B the correct answer. This question focuses on organic chemistry, specifically alkane, as well as hybridization and VSEPR theory. We start with the structure of butane. It's an alkyne which has a triple bond, which can appear between C1 and C2 or C2 and C3. Either structure will work to solve this answer. So we're going to go with the second one. All the single bonds connecting atoms are sigma bonds. In cases where we have double or triple bonds, those are made through pi bonds, and they only form after the initial sigma bonds. So the shortcut to hybrid orbital is to identify the type of bonds that's present and the geometry that's involved. For a tetrahedral shape with only sigma bond present, the hybrid orbital present in C is sp3. For a linear shape with 1 sigma and 2 pi bonds, the hybrid orbital present is sp. Here are the rest of the orbital hybridization cheat sheet so that you can use it for future reference. Now the correct answer is therefore the 1 and 3, sp and sp3 only. This next question requires Lewis structure and sigma and pi bonding knowledge. Start by analyzing the structure for each option. Pi bonding is present in structure containing covalent bond, so these two are out of the question. The first bond in covalent structure is always sigma bond. That means pi bond is present only in structure containing multiple bonds, which in this case is going to be C2H4. This question is testing on bond order and resonance. To figure out the bond order, we need to draw out all possible resonance structures. Here are the two possible resonance structures to represent formate ion. To calculate the bond order for X, we average out the bond for each resonance structure. The average of double and single bond works out to be 1.5 bond. Same goes for the Y bond order. For Z, the bond between CH is consistently 1 in both resonance structure, so therefore it's 1. The final answer is A, 1.5 for both X and Y, and 1 for Z. This next question involves formal charge, resonance, and bond order. Start by drawing all the resonance structures for phosphate ion. And it turns out that there are 4 resonance structures altogether for phosphate ion. To calculate the formal charge on oxygen, we total up the charges on oxygen, which is -3, and then we divide it over the number of oxygen atoms in each structure. So we have 4 oxygen atoms, so we have -3 divided by 4. Therefore, the formal charge on oxygen would be -0.75. To calculate the PO bond order, we total up the PO bonds in all directions, which in this case, in each structure, we have 5 bonds altogether for PO. And then we divide it over the total number of resonance structures, which in this case, we have 4, so we divide by 4. So 5 divided by 4 will give us 1.25. So the correct answer is C, -0.75 and 1.25. So how many questions did you get right? Here's the playlist if you need to brush up on any of the topics. I'll see you over there.